See, what is called, see, this morphism is a very important map which is called blow-ups. But to do in a complete generality, I need to define what is called rational functions, okay, or rational maps. Rational functions, you know, they are functions from an open subset to the underlying field. But what is called rational maps? But how they appear naturally in the example of blow-up. So, for example, if you take say affine space and take the product with n minus 1, Pn minus 1. In this, you take the subset, this is a closed subset given by set of points, say x1, xn. Take the product topology, not the product variety. And y1, y1, y2, yn. With the relation that xi yj is same as yi xj. I equal to 1 to n, j equal to 1 to n. So, first is that with this equation, this is a closed subset in the topology n cross Pn minus. So, B is a closed subset. So, this is closed. So, now from B to A n there is a map. The projection map basically. And but now the map pi is actually example of a rational map, right? So, or birational map, I'll say it's a birational map. So, I will come to the what is called birational, but if you notice pi, if you take a point, pi inverse of a point, if the point is, so there are two cases, if the point is 0 and if the point is not 0. So, first you see that pi if point is not 0, then there is a unique, so without loss of generality I can assume one of them y1 is 1, right. So, that will say that xi y1 equal to x1 xi times y1 if I put it equal to 1, then this is nothing but x1 of yi. So, if I fix a point x1, x2, xn, then yi is automatically getting fixed given by xi's, right. So, that says that the pi, if I take the point, if I assume, of course, the point is not, xi is now not 0. So, then the point of yi is uniquely determined, right. So, the pi inverse of point is a point, but if I take pi inverse of 0, then you will get entire projective space. So, this is a very peculiar, this is a very interesting map. This is called blow up of an at 0. So, pi inverse of point, if point is 0, if point is not 0, and this is equal to Pn minus 1 if the point is 0. So, that means that you have this affine plane, right, you have this point. So, this is basically a point, this is outside the point, it is the it's itself, but at the point 0, it's like it's a Pn minus 1. Say you are going to extra dimension. So it's blowing up the point. So that's why it's called blowing up the point. You take a point, you are blowing it up. So this is example, the simplest example of a blow up. And this is a example of a I will come what is called birational map. But you can do it more generally. For example, if you take a closed subset here in N, and here you take this blow up of 0. So I call this B. So this B, which I define. So this sometimes I call blow up of 0 of N. You are blowing up 0. Now you have this pi inverse. Now suppose the point 0 is in X. If 0 is not in X and X is a closed subset, X is a subvariety, affine variety, then pi inverse X is just a cup. It's because it's isomorphism, right, outside the 0. So that's not very interesting. But it becomes interesting when 0 belongs to X. Then what happened? Then you may not get the whole Pn minus 1. So what you need to, what is it called? So you consider pi inverse of X. And of course, this is sitting inside this. So if I take a closed subset by fiber, this is a fiber product with this. The inverse image of a inverse image of a subvariety or open subset. I mean, if you take something here map, then you take the fiber product. This also is a variety, and this is a. But this is not this need not be closed or in this topology. So what you need to take is the closure. So this is the definition of blow up at the point of 0 at X. Closure in this space An cross Pn minus 1. Now, of course, at the point other than 0, this is a pi inverse A. This is an isomorphism. But at the point 0, you have a non-trivial fiber. So once we do some examples, we will see how things. But this blow up thing is very useful in resolution of singularity. As I was saying that if you take a curve here, now when you do blow up, then what you get a curve like this. So the singularity is resolved. In the case of curve, when dimension of X is 1, smooth projective curve, then blow up. If you do the blow up, you do the resolution of the singularity gets resolved. But in a higher dimension, it is not true. The idea is that by blowing up, because you are attaching a point to some solid space. So idea is that by doing this, you can remove the singularity, and this is called desingularization of a singular space. So like I was saying, the characteristic 0, it is known that by successive blow-ups, you can do you can succeed. But in characteristic P, it is not known whether successive blow-ups will give you. See, you have to choose. See, the point is that, the point, if some point is singularity, that point may not be the only singular point. That may have a subvariety may be a singular subvariety, right? Singular set, after all, it's a closed subset. The closed subset may not be a point. It may be a sub-variety. So, of course, if that is the case, then removing that kind of singularity is much difficult, right? Then you have to blow up a curve. It's just a point. What I'm saying, but you have to then blow up a curve. So such things are also there. Such things can be also done. But before going to any example of blow up, and I first have to need to say what is it called rational maps, at least in affine case. Okay. So see, if we have a suppose x, we are in affine, quasi affine, x y quasi affine varieties. So I say that a map, a rational map from x to y, if it is not over whole x but over a open subset. Suppose x y quasi affine irreducible. I mean, we are in nice situation. So this so if there is a map from f from u to y, then I call f is a rational map. Upper is one is dotted one, and this one is the solid one. So dotted one means it's not the map over the whole x, but it is on an open subset. As you, so then you say f is a rational map. It is just like rational function. In the case of rational function, what you know that it's a map from the open subset to k, right? You generalize that too for morphism of varieties. So rational map is not a morphism from the whole x, but it's a morphism from the open subset. Right. Now the point is that if I take dominant rational map, so dominant rational map means f of u closure is y. See, without loss of generality, whenever you have a morphism from x to y, I can forget the so this is Chevallier's theorem that image of a constructible set is constructible. So, so it's enough to, I mean, you can forget the closure of the image. Image may not be closed. If image is closed, then you are in good shape. The image may not be closed, right? Like for example, you saw the example a2 minus a2 to a1. You take the hyperbola xy equal to 1, the image is a1 minus 0, image is not closed, right? That map is not proper. So, but you take the closure and then rest you forget, because that is not in your hand, your f is not related. So, without loss of generality, we can always assume that these maps, morphisms are dominant. You take the image, then take the closure, that is your y prime. So, x to y, if I have any morphism, what I am saying, x to y, if you have a hemimorphism, then consider fx the image and take the closure, which is sitting inside this. So the f actually taking is a morphism from x to fx bar. Y I can forget now. So without loss of generality, so dominant maps are not. I mean, they are good enough. I mean, when you study maps, enough to work with dominant maps. Right. So this is dominant means that fx closure is y. This is called dominant. If fx, if you take the image, take the closure, that is equal to y. Then dominant rational map means you take the image of u, and if its closure is y, then you call it a dominant rational map. So then it's called dominant rational map. But good point is that if I have dominant rational map, see, I want to have good to do some mathematics, you need to compose functions, right? Like whenever you want to define some category, you need to compose two morphisms, right? So now the point is that if I have two maps f from y to x to y, and y to z, then how do you compose? So, you need to know that f of x, the domain of G should be inside image of f, something like that, right? Because it's not a map from x to y, so you need to be little careful. But the point is that if it is a dominant rational, if you are in the category of dominant rational map, then this is well defined. You can define. So, if G is also, if G is a rational map, say V to Z, and F is dominant, then you can define G composition F to some. So, you take the FU, take the FU, since FU closure of is Y, so FU will intersect V. After all, V is an open subset. So, V will, so take the intersection and define, yeah. So, define a, so for the, so what I am trying to say, in the category of dominant rational map, the composition is well defined, right. So, what I am saying that category, so I denote this category by rational, RAT, rational map between x and y. So, this is the category. So, x, y are quasi-affine. So, objects are quasi-affine varieties, and morphisms are morphism between this are denoted by this dotted arrow. F is dominant. Dominant rational. By the way, here also you have to be a little bit careful. Here on this you have to put a equivalence relation. Equivalence relation in the sense that if you may have two rational maps, say F and G. Suppose A. So when you have a map F, so it is basically a map from U comma F, right? A map from U to Y. Similarly, if I have a map from V comma G, I say the F is equivalent to G if F equal to G on U intersection V. Because then F and G are given by same, so then you say that they are same, right. So, yeah, so in some sense that if I, if I have a rational map, if I have a rational map U1 to F Y, so U1 is in X. Similarly, if I have F1 and if I have another U2, which is also a open subset here, to Y. Suppose F1 U1 intersection U2 is same as F2 U1 intersection U2. So, then I can define F to be F1 union F2, because these are all continuous functions. So, if I have two functions, if they matches, if I have two open say U1 and U2, if you have two functions F1 and F2 which matches on U1 intersection U2, you can define F to be on U1 union U2. So, without loss of joint, we can assume that these U's are maximal open subset. So, in that sense, you can assume that my element, when I take a element here, these are rational functions, that F is represented by U comma F. There is no uniqueness, but without loss of joint, you can assume that the U is the maximum where F can be defined. You understand? So, this is the equivalence relation. So, element here is a you can think that this is a maximal open subset where this function can, after this you cannot define the function. Okay. So so with this little bit of subtleness is there. So when you give a rational map, that map is actually not unique in the some sense. It is an equivalence class, but in this sense, it is, you can take the maximal open subset where the function can be extended, right? So the point is that, so the theorem in this thing is that I can consider this category of quasi-affine variety. See, in the case of affine varieties, you know that the morphism of affine varieties corresponds to finitely generated algebra. That category of affine varieties and category of finitely generated K algebras, reduced K algebras, these are equivalent. So now the question was that if you take, instead of affine, if you take quasi-affine, whether you have any such, because quasi-affines are not affine always. So quasi-affine varieties, whether you have any such categorical equivalence. So, but not for the function, not for more, but if you take the rational, for example, every map from x to y is a rational map, right? If I have a map from, if you have a dominant map from surjective map, say, or dominant map from x to y, that's always a rational map because you take x to be u. That is also a in the category. So this category, the dominant rational. So you consider this category say this. How do you denote the category of say rational? Let's call this rat. Quasi-affine. So this is quasi-affine objects are quasi-affines, and morphisms are dominant rational. Now, if you have any dominant map from affine variety, quasi-affine varieties, that is also a rational map. So now the point is that this dominant, this category, this dominant, this rat category, there is a one-to-one correspondence with finitely generated finitely generated field extensions of K. So that means these are, so basically you take X and you consider the function field of rational function. So if X and Y are birational, so okay, before that I should say what is birational. This is a theorem, so I will come to this. So what is called birational? Sorry, this map F is birational. So when I write like this, that means F is a map from U to Y. So this is birational if there is a map G from Y to X such that G composition F is birational to identity. So this is on X, and F composition G is birational to identity Y. So it's not equal to, but it is on equal to on an open subset. Yes, equivalence, that F is equivalent to G if they are equal on some open subset. So that same equivalence. G composition F is a map from X to X. So it is on an open subset, it is identity. So now, this is then if this happens, then you say the f is birational or x and y are birational. It's like isomorphism. So now you have this category of this category quasi-affine varieties with dominant rational map. That is one-to-one correspondence with finitely generated field extension of K, and morphisms are map of fields. So this is a theorem. So this is a major, like this was a natural question that in the case of quasi-affine variety, what happens if you just, what is the morphism category of quasi-affine variety? But you need to be little careful. You have to take a dominant map. But dominant maps are not bad, because after all, when you consider morphism, it's not the entire image. You only are interested in image and around image. The around image means the closure of the image. Outside the closure, this is not in your hand. So it's not bad. I mean, so dominant rational maps category in the quasi-affine variety and dominant. This is as a one-to-one correspondence of finitely generated. This is a major theorem. Like, but I don't have sufficient time now to prove this theorem. It will take some time, but this is a fact. Yeah, these two categories are equivalent. So birational classification is basically field theory, basically, in broad sense. For quasi-affine, of course, not for any variety, quasi-affine. Okay. Okay. So now some examples of so for example, of course, if you take any variety, say X, if you take open subset, this is a birational. Take the inclusion, because you define from X to U the same map, identity map on U. So inclusion map is always a birational map, right? This is a, so inclusions are always a birational. Inclusion are open or open immersions are birational. Inclusion, so I will not write many. Another, for example, affine space. So, but okay, I was saying about quasi. So theorem I stated for quasi-affine varieties, but this when I define rational map, you can define it for any variety, irreducible variety. Same definition, that if x and y are, if x, y, any variety, any algebraic variety, then same definition will work. That if I say a map, a rational map means it's a map from U to Y, where U is open subset. Assume X is irreducible. So similarly, all these things, the definition of rational map does not depend, just like in the case of variety, the regular functions or rational functions, they don't depend on the whether you are working in affine variety or quasi-affine. But the theorem is only for quasi-affine. That is fine. This theorem is only for quasi-affine category. But rational maps make sense for any variety, any algebraic variety. Right. So in that sense, in the affine space and by the projective space, they are birational. So A n and Pn, this is birational. There is a natural map, right? That you have some identity, An is isomorphic to some ui. There are plenty of maps, right? Phi I or psi I. The standard affine cover of Pn, and that is an open subset. So that's a birational map. So this is birational. So An and so Pn and so up to birational. So the point is that see in any subject, like in topology, you want to study, you want to know what are the isomorphism, or in group theory, isomorphism classes of groups, right? Finite groups. So that's how the subject developed. So in topology also, you want to know whether the homeomorphism, what are the homeomorphism classes of topological space. Similarly, in algebraic geometry, you want to know isomorphism classes of algebraic varieties. Can you classify them? That I give you a dimension, say n, can you classify some type of algebraic variety up to isomorphism? Answer is difficult. Like topology, like group theory, everything, like any classification problem is difficult because it becomes huge collection. So how do you classify? So, but this classification, this birational classification, little weaker classification, right? If x and y are isomorphic, then of course they are birational. But if they are birational, for example, An and Pn, they are birational, but they are not isomorphic as varieties. So birational classification is little weaker. So now the question, next point is like homotopy. In topology, you say homotopy classification, x and y are equivalent if they are homotopically equivalent. So whether can you classify up to homotopy equivalence? If two topological spaces are homotopy, their fundamental groups and all are same, right? Topological some invariant, these are homology groups or fundamental groups, they are same. So that's why, so these are invariants up to some equivalence relation. So similarly here, the question is that can you classify algebraic varieties birationally? So up to dimension 3 it is known, this is the result of Mori, but after dimension 3 it's not known. These are all unknown. Even birational classification of algebraic variety, projective variety, I assume projective also. Dimension of the underlying variety dimension, it's not known. So dimension 3, dimension 2 it was known before. Classification of smooth, assume smooth also. X is smooth. That means all don't bother about singularity. So these are all difficult problems to work on. But can you classify such objects? So for surface case, it was known long back in 19th century, late 19th century by Italian geometers. But it took algebraic curves, it is quite easy. So actually every equivalence there is only one non-singular curve up to, if you assume that x is smooth, then for every in every class you have only one object up to isomorphism. In surface, it was done by Italian algebraic geometers. So it was known in late 19th century or beginning of 20th century. Curve dimension 3 it took long time. It not late 19th, but I think early 20th century. I am not sure about the dates for surface. Enrique Severi, probably not early, I think middle of 20th century. Just somehow. Anyway, so for dimension 2, but dimension 3, this was proved by Mori. So Mori gave some algorithm. It's called minimal model. So after his discovery, it is named after minimal model or Mori minimal model program. by which you classify your algebraic smooth projective threefolds, 3 dimension 3. But after dimension 3, it's not kind of, it's open thing, not much is known. Okay. So, so the point is that this birational classification itself is difficult. Nothing is easy. So even whether a two variety is given to variety, whether they are birational or not, these are not easy questions. So that's why it's called birational geometry. There is a big field of the big chunk of work going on in algebraic geometry, which is called birational geometry, and they study these kind of questions up to birational equivalence. Okay. So now why I did all, but I will not probably prove this theorem. This is a very important theorem, but I will not prove this theorem now, but I will come back to now blow up. And then what I want to say that these blow ups are the examples of birational maps. And these blow ups are important because this gives you, first one is that it gives another, starting a variety, you blow up at some point or some sub variety, it gives you a new variety, which is interesting, which is birational to the given variety. So if you have a variety which has some singularity, so the idea is to you blow up the singularity set, the whatever you get, you expect it to be non-singular, or at least some level of the singularity gets diminished or something. In the curve case, it is always the case, but not in a higher dimension. That blow up, not just one blow up may not be enough. You need to do many blow ups. Okay. So I will continue in the next class. And then I will come to the morphism of smooth maps. So this is, so far I have not said anything about morphism, smooth morphism. I am mostly talking about the singularity of a variety and all. So then next is the singularity of a morphism. So in particular is it that will be the singularity of a underlying variety. And then I will stop.